So in the next lectures, I will develop some techniques in order to solve the following equation. So I will consider G an open, connected subset of Rn. Actually, n will become 2, but for the moment you can think that you're working in any higher in any dimension. And on this open and connected set, I will consider function f, taking real values, which is of class, well, maybe C. So C will represent the functions which are continuous. And then I will represent by delta G the boundary of G. So the boundary of G is the set of points which belong to the closure of G and do not belong to G. So bar G is the closure, and the boundary will be the closure minus the set G. And I will consider second function, which is defined on the boundary of G, which takes real values, and say that it's also continuous. I will assume always that the boundary of the set G is a smooth surface. So once you fix these two functions, I want to consider the following problem, which is called the Poisson equation. So I'm looking for a function u defined on the closure of G, such that minus the Laplacian of u, it's equal to f, and this is on the set G. And then u, I want u to be equal to G on the boundary of G. So let me tell you what a Laplacian means. So a Laplacian of a function u at a point x will be just the sum from 1 up to n of the second derivatives. So let me represent by delta xj the first derivative, delta 2xj the second derivative in the j direction of the function u, and this computed at x. So this is a differential operator, and we want to find a function u such that minus its Laplacian it's equal to f on the set G. So this holds minus Laplacian of u at x, it's equal to f at x for all points x in G. And u of x, it's equal to g of x for L or all x in the boundary. This means that I'm looking for a function u which is twice differentiable on G. So I will represent by C2G the functions which are defined on G and which have two derivatives in any directions. So I want that the xi, the xj to be well defined, and that this function to be continuous. So saying that u belongs to C2G means that u has two derivatives in any direction, and that the second derivatives of u are continuous functions. So I want a function u which belongs to C2G, so that when I take its Laplacian, I get a continuous function, and I want this continuous function minus this continuous function to be equal to f on the points of G. And I want also this function to be continuous up to the boundary, so that it makes sense to say that u is equal to G at the boundary of G, because here we have two functions which are continuous at the boundary. So the problem is, given this open connected set G, given two functions f and g which are continuous, find a function u which belongs to this set, so it's twice differentiable on G and it's continuous up to the boundary, such that minus the Laplacian of u it's equal to f on the set G, and u it's equal to G at the boundary. So this is the problem which I want to solve. In order to do that, we will proceed. That will take, I think, 3 lectures. So in this lecture, what I will present, it's a general variational problem on Hilbert spaces. So I want to, in this lecture, formulate a quadratic variational problem on a Hilbert space and show that it has a unique solution under certain conditions. So this will be done in this lecture. It's a total general statement on Hilbert spaces. Then in the following lecture, I will define some Sobolev spaces. And I will show that these Sobolev spaces are related to the solution of this equation. And finally, in the third lecture, I will prove existence and uniqueness of solutions of this equation in these Sobolev spaces. So here in this lecture, I will forget about this elliptic problem, and I will consider a general problem on a Hilbert space. I will solve that, and that will be used later in order to solve this equation. So let me turn to a general theorem. X will be a Hilbert space. And on this Hilbert space, I have a function a from x to the real numbers. And I will assume that this function has some properties. So the first one is that ax will be linear, so that a is bilinear. We have already seen what is bilinear, but let me just say it again. So this means that a alpha x plus y z it's equal to a alpha a x z plus a y z. And this for all real number alpha x, y, z in x. And that a of x alpha y plus z it's equal to alpha a x y plus a x z. So I will be assuming that this functional a it's bilinear. I will assume that it's symmetric, which means that axy it's equal to ayx. I will assume that it is bounded, which means that there exists a finite constant C0 such that axy it's bounded by this constant C0 times the norm of x times the norm of y, and this for all xy in x. So this constant is of course finite. So this is bounded, what I mean by bounded. And finally that it's coercive. And this means that there exists a positive constant C1 such that axx it's bounded below by this constant C1 times the norm of x squared for all x in x. So these are the four assumptions I will assume on this functional a, which is defined on x times x and take values in R. And besides, I have a function b, which is defined on x and take values in R. And this is simply bounded and linear. And so the theorem reads as follows. So assume that I have a function a which is bilinear, symmetric, bounded and coercive. I assume that I have B, which is bounded and linear. Then what I claim is that if you take the infimum, consider the following variational problem, infimum of 1/2 of AXX minus B of x for all x in my Hilbert space X. What I claim is that this variational problem has a unique solution. So it has unique solution. And this is the theorem I want to prove. So that if A satisfies these properties, if B is a bounded linear functional, then this variational problem has a solution, and this solution is unique. So proof of this theorem. So the proof, I'll start with the existence. So I want to prove that this variational problem has a solution. So there is one x which minimizes this functional. So let me call that functional f of x. So this is 1/2 of AXX minus BX. And let me call alpha the infimum. So first, I claim that alpha it's larger than minus infinity. So alpha can't be, this infimum can't take the value plus infinity. And why is that so? Well, take f of x. So f of x is given by this expression. So now I know that A it's coercive, which means that f of x it's larger than 1/2 C1, the norm of x squared. This because A is coercive. And now B it's bounded. So B it's bounded by B of x. It's less or equal than a second constant C2 times the norm of x. So this expression it's larger or equal than minus C2, the norm of x. So now if I compute f0, what I claim is that this expression it's larger than f0 if the norm of x it's large. Because as the norm of x converges to plus infinity, this expression here, since C1 it's strictly positive, converges to plus infinity. So this means that f0 it's a number. And what I'm saying is that, well, if the norm of x it's larger than r, then this expression it's larger than f of 0. So what this implies is that there exists r such that if x it's larger than r, then f of x it's larger than f of 0. Right? The limit of this expression as the norm of x tends to plus infinity, it's plus infinity. So this means that there exists an r such that, well, if the norm of x is larger than r, then this quantity is larger than f0. And this is telling me that, well, if I want to compute this infimum, well, I can restrict the infimum to all points x whose norm it's bounded below by r. Because if the norm is larger than r, then f of x it's already larger than f0. So this is telling me that actually this alpha, in computing this alpha, I can restrict myself to the points in which f of x has norm bounded by this r. Well, and now this infimum, it's clearly, so this infimum, it's clearly bounded. So this is, now we have seen that f of x, it's bounded by that. So alpha, it's larger or equal than the infimum of 1/2 c1 theta square minus c2 of theta, where theta is bounded by r. Right? F of x, it's larger than this expression here. So the infimum of f of x, for x bounded by r, it's larger than the infimum of this expression if provided I take theta to be bounded by r. And this is, you can compute it, this is strictly larger than minus infinity, which shows that indeed alpha is strictly larger than minus infinity. So up to now, I introduced this functional f, which is 1/2 of a minus b. And I defined alpha as the infimum of f on all space. And I proved that this infimum is strictly larger than minus infinity. So my second step is to find a sequence un which approximates this value alpha. So there exists, since this value is strictly larger than minus infinity, there exists a sequence un in x such that f of un converge to alpha. Of course, alpha, it's also strictly bounded by plus infinity because it's an infimum, so alpha, it's smaller or equal than f of 0, which is a real number. So since alpha, it's a real number, I can get a sequence un in x which approximates alpha. And what I want to prove, so my claim is that un is a Cauchy sequence. So this is what I'm going to prove now. So I want to prove that un, it's a Cauchy sequence. Un is the sequence such that f of un is converging to alpha. In order to prove that it's a Cauchy, let me write f un plus f of un. So this is equal, by definition of u, of 1/2 of a un plus b minus, b of un plus 1/2 a um minus b of un. So now I will write this as a of un plus over 2, un plus over 2, plus ua of un minus over 2, un minus over 2. And you see that when I write these first two terms, I get here un divided by 4. When I remember that a, it's linear on each coordinate, so if I expand this, what I will get is that a of un, a twice, and a So let's see un, I get here a term with factor 1/4, and here also a term with a factor 1/4. So 1/4 plus 1/4 will give me the 1/2. And the same thing for I have 1/4, with a plus sign 1/4. So this will give me, so the two diagonal terms in this expression give me the first two terms. And then the off-diagonal terms vanish because I have here un with a plus sign, while here I have un minus with a negative sign. So the sum of these two terms give me these two terms. And what remains, it's bun minus um, I'll write that as minus 2 times b of un plus um over 2, because b is linear. So now if you go back to the definition of f, so let me write here 2 times 1/2. And what appeared here is that I have this term here and this term here, which give me exactly f of un plus um divided by 2. So let me write these two terms with a 2 in front, 2 times f of un plus um divided by 2. Right? This is, I have a 2, 1/2 of a un plus um, and here 2 minus b of un plus um. So this takes care of these two terms, and then I have a plus a of the difference. So for the moment, I just have identities. I proved that f of un plus f of um can be rewritten as 2 times f of un plus um divided by 2 plus a of un minus um divided by 2, un minus um divided by 2. Now, let me use the property that alpha is the infimum. So f of this point, it's bounded below by alpha, because alpha is the infimum. So I have here, this is bounded below by 2 times alpha. And let me use also the fact that a is coercive, so that this expression, it's bounded below by a constant c1 times un minus um divided by 2 square. So up to now, I proved that f un plus f it's bounded below by 2 alpha plus c1 times un minus um divided by 2, the norm of that square. So let me just rewrite this inequality here. So this is 2 alpha plus c1 un minus um divided by 2 square. So I rewrote here the inequality we proved. So now let's remember that f of un is converging to alpha. So if I send n to infinity, this expression is converging to alpha. That one is converging to alpha. Here I get 2 alpha. So this shows that un minus um divided by 2 square converge to 0. As n and m tend to plus infinity, this expression has to converge to 0 because it's bounded by it's positive and bounded by an expression which converge to 0. And this proves that indeed the sequence un is Cauchy. So now let's complete the proof of the existence. Since un is Cauchy, un converge to some u. And what I claim is that f of u is equal to alpha. And this comes from a lemma, which I will prove after the proof of this theorem. This lemma tells us the following. Well, assume that A satisfies the assumption of the theorem, so the 4 assumptions. What I claim is that if I have un converging to u and vn converging to v in X, then A of un, vn converge to A u v. So this lemma, it's very easy to prove. Let me assume from now, and let me complete the proof by assuming this lemma, which, as I said, I will prove at the end of the theorem. So we know that fun converge to alpha. F of un, it's 1/2 of A un un minus b of un. Now, un is converging to u. So by the lemma, this expression is converging to 1/2 of a u u. B, it's a bounded linear functional. Un is converging to u, so this is converging to b of u. And this is f of un, which is converging to alpha. So from these limits, we get that indeed f of u is equal to alpha. So we proved that there exists a point u in x such that f of u is equal to the infimum, so that this variational problem has a solution. Well, to prove uniqueness, let me observe the following. So assume that x0 is a solution, then I claim that a x0x minus b of x, that this is equal to 0 for all x in x. And this is the Euler-Lagrange equation for this variational problem. So I will just repeat the argument I used for the Dirichlet problem. So let's assume that x0 is a solution, so that x0 minimize this functional. This means that if I fix any x in x, what I have is that f of x, it's or f x0 plus t of x, that this is larger than f of x0. Which means that this functional, let me call phi of t, which is f x0 plus t of x, has a minimum at t equal to 0. So let me compute phi of t. Phi of t, which is f x0 plus tx. Well, by definition, this is 1/2 of a x0 plus tx, x0 plus tx, minus b x0 plus tx. So now let's use linearity to write that as 1/2 of ax0 x0 plus t a x0 x plus t2 over 2 a xx minus b of x0 minus t b of x. So this is the function phi t. You see that phi t is a polynomial of degree 2 in t, so it's differentiable. And since phi has a minimum at t equal to 0, we know that phi prime of 0 is equal to 0. So now if I take phi prime, so if I compute here what is phi prime of t, this first term doesn't depend on t, so it disappears. This one, the derivative is just 1. This one gives me t. This one doesn't depend on t, it disappears. And this one, the derivative is 1. So here is the derivative of phi at t. Now let's compute that at 0. So phi prime at 0, this term will disappear. And therefore, the equation that phi prime of 0 is equals 0 tells me that indeed a x0 x it's equal to b of x for all x. Because in this argument, this is true for any x. So up to this point, I indeed proved that if x0 is a solution, then a x0 x it's equal to b of x for all x in x. So this is what I wrote here, x0 a solution, then a x0 x it's equal to bx for all x in x. So to prove uniqueness, assume that you have two solutions, x0 and x1 solutions. By what I just proved, I know that ax0, x, it's equal to bx, and this is equal to ax1, x, for all x in x. So this means by linearity that ax0 minus x1, x, that this is equal to 0 for all x in x. So if I take x to be x0 minus x1, what I get is that ax0 minus x1, ax0 minus x1 is equal to 0. But now if I use that A is coercive, this means that this is bounded below by C1 times x0 minus x1 square, and therefore the norm of x0 minus x1 is 0, which means that x0 is equal to x1, which provides uniqueness. So this completes the proof. We have just proved that if A is bilinear, symmetric, bounded and coercive, and B bounded and linear, then this variational problem in a Hilbert space has always a solution, and this solution is unique. So I owe you a lemma, and the lemma was saying that if I have A satisfying the assumptions of the theorem, so the hypothesis of the theorem, and if I have xn converging to x and yn converging to y, then axn, yn converge to axy. Okay, and we'll see that we don't need whole hypotheses of the theorem. We just linearity and boundedness. So let me prove this lemma. So I want to compare axn yn to axy. So let's write this difference. So this is bounded by axn minus x yn plus ax yn minus y. And now let's use the boundedness, which we did not use up to now. So let's use the boundedness. So here we use linearity. Now let's use the boundedness. So this is bounded by a constant. C0, I think, was the name of this constant, times xn minus x, the norm of that, times the norm of yn, plus the same constant C0 times the norm of x times the norm of yn minus y. Now, if we let n to infinity, this is converging to 0 because xn is converging to x. This is converging to the norm of y, so the product is converging to 0. And here also, since yn is converging to y, this is converging to 0. So this proves that indeed this difference converges to 0, which means that axn yn is converging to axy. And this completes the proof of the theorem. And I have a corollary to that theorem. We have already seen that if x0 solves the variational problem, let me call VP this variational problem. So if x0 is the unique solution of this variational problem, we have seen that ax0x is equal to b of x for all x in x. So that we proved during the proof of the theorem. Now what I claim is that the opposite, the converse, it's also true. And so suppose that there exists x1 such that ax1 x is equal to b of x for all x in x. What I claim is that then x1 solves the variational problem that we wrote. So I'm assuming that ax1x is equal to b of x for all x in x, and I want to show that x1 is a solution of this variational problem. Well, what I have to show is that x1 plus y, 1/2, x1 plus y, minus b of x1 plus y, that this is larger or equal than 1/2 a x1 x1 minus b of x1. Right? I want to show that x1 is the solution of this variational problem, so f of x1 has to be less or equal than f of z for any z, but any z can be written as x1 plus y. So this is what I need to prove for all y. So now if you expand the first term, you see that, well, we have a diagonal term which will cancel with this one. So there is the other diagonal term, so which is 1/2 of a y. Then I have twice the off diagonal term, so plus 1 times x1 y, minus, here b it's linear, so bx1 will cancel with bx1, and what remains is b of y. So this inequality is true if and only if this one is true. But now let's use the property of x1. We know that ax1x is equal to b of x. So this means that this term here it's equal to 0. And therefore, this inequality holds if and only if 1/2 of a y is larger or equal to 0. But that we know because a is coercive. So this indeed proves that if ax1x is equal to b of x for all x, then x1 is indeed a solution of the variational problem. So let me emphasize our last result. We have just proved that a solution of this variational problem, so x0 is a solution of this variational problem in the sense that this functional takes its minima at x0 if and only if x0 is the solution of this equation. So we have two versions of the same problem in a sense. So a solution of this equation is a solution to this variational problem, and a solution of this variational problem is also a solution to this equation. So we can formulate the same problem in two ways, either by considering this equation or by considering this variational problem.